It is now time to cover another very important concept in physics, namely coordinates. To some, it might seem like a trivial concept, but there are countless of coordinates to use, and for every situation, a specific choice of coordinate system may be better than another one. Today, we will also discuss the concept of dimensions and some of the most basic coordinate systems and its relation to vectors. The first question one can ask is, what is a coordinate system? It is simply a system that uses one or more numbers to determine the position of a point in some space. In classical physics, one often considers the three-dimensional Euclidean space, and it's arguably the simplest space conceptually as it resembles the space that we experience in our everyday life. In this space we have length, height, and depth, the three dimensions of space around us. The first coordinate systems which most people are introduced to in school or high school is the Cartesian coordinate system. For simplicity, we can consider the two-dimensional Euclidean space. Now you can draw your coordinate system with some origin and then make a dot at some point with coordinate 2.1. With such a coordinate, you know that to reach the point, you need to move 2 units along the length and 1 unit along the height when starting from the origin. Thus, coordinate systems gives us a mathematical tool to describe a position in space. The three-dimensional case would work in a similar way, but you should additionally specify the depth also. Now we have already started talking about dimensions, and dimensions can be understood as how many numbers or coordinates you would need to describe one point. So in a one-dimensional space, which is just a line, you would need one coordinate to describe a point along the line. In 2 dimensions, you would need 2 coordinates to describe a point on a plane. In 3 dimensions, you would need 3 coordinates, and so on and so forth. But you may notice that because we live in a 3D space, our brain can't really comprehend a 4-dimensional space. But in mathematics, it's very simple. You just need to add one more coordinate for every point. You might think, great, we have Cartesian coordinates, and with them we can describe points in 3D space. Why do we need more coordinate systems? The answer is simple: convenience and understanding. If you ever study general relativity in detail, you will realize that the choice of coordinate systems changes what information you can obtain from the system. In some coordinate system, you might get an infinity at some location, but using different coordinates, you will not get an infinity at the same location. Sometimes infinities just mean that you chose your coordinates in an undesirable way, but it can also indicate that something special happens at this point, like it could be a point of a black hole. We will talk about this more when we get to general relativity. Let's consider a simple example of why using different coordinate systems for different applications is desirable just from the point of view of convenience. To keep things simple, let's only consider 2D coordinate systems for now. If you want to describe a rectangle on a 2D plane, then Cartesian coordinates are great because you can describe the 4 corners of the rectangle with 4 coordinates, let's say 0.0, 0.1, 2.0 and 2.1. Then a line between the points will give you the rectangle. In conclusion, Cartesian coordinates work well for objects which are made from straight lines. This immediately leads to the question, what to do if you want to draw circles? While it's still possible to continue with Cartesian coordinates, it's much simpler and intuitive to use what's called polar coordinates. A polar coordinate contains a radius and an angle. So if you want to draw a circle, you just have to choose the radius we would like, let's say 2.0. And then one just draws a line following the full 360 degrees of the circle. By adding another angular coordinate, one can get a 3D sphere in a similar way using what's called spherical coordinates. We talked in a previous video about how some quantities are scalars, meaning just a number like temperature, and some quantities are vectors. A vector is defined using coordinates, and one can choose different types of coordinates as it suits the situation. Let us consider the quantity velocity. If you say you travel at the velocity of 5 km per hour, you're referring to the magnitude of the velocity and not specifying the direction. Consider the two-dimensional case with Cartesian coordinates. Then we can define the velocity in terms of its component in the x and y direction of the coordinate system. It would be trivial if the velocity only had a component along either the x or y direction, since the component would be equal to the magnitude. So let's say that our velocity is such that we move 4 km per hour in the x direction and 3 km per hour in the y direction. This can be expressed as the vector 4.3, which magnitude is found using Pythagoras. So the magnitude squared is equal to 4 km per hour squared plus 3 km per hour squared is equal to 25 km per hour. And to find the magnitude, we square that, so we found the magnitude 5 km per hour. But now we also know the direction of the vector. Now, if you didn't want to do all this work, you could just have used polar coordinates. Remember that the first coordinate is the radius, but the radius is just the same as the magnitude of the vector. So in polar coordinates, you just have to figure out the angle which matches the direction you want, and you're done. A final note about vectors is that we can add and subtract vectors by simply considering the components of the vector. Suppose that we want to add two vectors 2.3 and 4.2, then we can just add the x components and add the y components. So 2 plus 4 is 6 and 3 plus 2 is 5, and then the magnitude is found again using Pythagoras. 6 squared plus 5 squared is 61 km per hour, so the square root is then the square root of 61 km per hour. Subtraction works in a similar way. Note that one can't just divide or multiply vectors, but you can do other operations such as obtaining the cross product and the dot product, but let's not get into that today. To summarize, in this video we have discussed how dimensions affect the number of coordinates we need to describe a point in a coordinate system. We have also discussed the most well-known coordinate system, namely the Cartesian one, and how we need a space to use our coordinate system in. We have discussed how important it is to choose an appropriate coordinate system for a given task, and consider simple cases with polar and Cartesian coordinate systems. Finally, we discussed vectors and addition of vectors. With all this new knowledge, we are ready to tackle the next video about the Lagrangian formalism of classical mechanics. If you like this video, feel free to like and subscribe. You're welcome to comment on what you like and disliked. As always, stay tuned for more.